I noticed this thing during Gary Hinshaw's talk, that that the ratio of experimentalists to theorists in this room is about the same ratio as the scalar to tensor to scalar modes. I worried a little bit about that. As the upper limits get better, what's going to happen to us?
But you also noticed in Gary Hinshaw's talk that ratio rose a lot.
Well, in different theories. Anyway, that's me. I would say most of the things I actually know about is nothing to do with quantum mechanics or gravity, although I work on gravity experiments. I would say my one-liner is my job is to reduce classical noise in complicated experiments. So that's where I'm coming from. And so I got, at the beginning, when I first got to Caltech, I thought the right thing to do would be to test quantum mechanics and to see if I could figure out experimentally, is there any nonlinear effects in quantum mechanics, because I had read Weinberg's paper. But like a poor student, I hadn't read any of the follow-on papers that pointed out the problems to nonlinear quantum mechanics. But I was talking about this a bit, and John Preskill was in the audience, and he said, you go to the library, young man. Read about this a little bit. And of course, so there's the stuff that's been mentioned by Yanbei about Polchinski and Jisan and so on. But I drew this cartoon. This is based on Scott Aronson's blog, where he says, quantum mechanics is an island in theory space. And I've asked Carl Caves and Scott also, I said, what are we going to do about this? How do we get beyond quantum mechanics? Because there's I think, very well-formulated arguments against any extensions to quantum mechanics. And my colleague at Caltech, Anton Kapustin, has written a vast mathematical treatise about, which says, just give up. It's not going to happen for you. And I said, Anton, I don't understand what you're saying. And then he wrote a one-page, I think not in response to me, but in response to others, a one-page intro which says, sort of like this, if you don't understand the rest of my paper, here's the intro, which is still over my head. So I still yet need another bridge to get there, but this is the sort of landscape. And if you noticed, I've pointed the frontier of quantum gravity is in the shape of Canada. And I change this depending on where I am. But I feel a bit like, yeah, we're worried about this thing. There's sharks and things here, and if we step off of our islands, which are comfortable, yeah, it's dangerous out here. And at the beginning, our theories won't make a lot of sense, and maybe they'll be internally inconsistent. But I think we have to try in any case and just suffer for a bit before we get to the promised land of Canada. That's maybe I should end the talk there. I don't know. So I don't know much to say about quantum gravity besides I just sort of follow what other people are doing, and I wonder what to do. I think that's the only reason I got seduced into gravitational wave experiments in the first place is my advisor said to me in 1998 or something, yeah, this is a great time to enter into this field, and within 3 years we'll have a detection, and we'll be looking right at the edge of black holes. And I said, 3 years? That's way better than these people doing dark matter and the Higgs boson or something. I think 3 years is fine for a PhD, and I'll be done with a detection during my thesis. But the road was longer, as I found out. And so, and my main aim was to see, like, is the black hole horizon really classical, or is there crust around it, or that sort of thing? And in LIGO, we are far, far from measuring something like that, although we aim to do it, and we do it by essentially consistency checks. So we look at the post-Newtonian form of the in-spiral, and then we look at the quasi-normal modes of the black hole ring down, and we look for consistency between these two parts and see, is there anything else going on? Is there energy lost, energy gained, angular momentum? Does the entropy increase as we expect, that sort of stuff? And so far, there's nothing, nothing surprising. Everything is consistent with relativity. And I thought, let's see if I can read my slides. There's these interesting previous experiments. We have the Hulse-Taylor binary, which probably since 1980 has just been getting more and more precise, and all of the other Hulse-Taylor like binaries out there have been showing us that at least at the source, the radiation is about what you would expect if you know what the motion is. LIGO has placed limits on the speed of gravitational waves. which sort of gets better with time, but it's of order. The difference between v of gravitational waves and c is about 10 to the minus 15 or less. So that, and undoubtedly will get better, but requires us to measure both gravitational and electromagnetic sources at a larger distance. And the one source that we had to put this constraint was the binary neutron star merger in 2017. That was observed by something like 1/3 of Earth's astronomers. So it was very popular. It was difficult to write that paper. There's a limit. As you get something like a few hundred co-authors, it's really difficult. And then when you get to 1,000, it's kind of impossible. And then beyond 1,000, nobody even knows what it's like the whole world is part of your co-author list. You don't even need an author list anymore. And then, of course, there's near-field experiments have been going on, the Edvosh group, and then finally there was the work from Aaron Kapitulnik, I think, at Stanford, who had extremely short-scale cantilever measurements. And those have also, they've run into the problems that we just heard about with short-scale electrostatics, patch potentials, Casimir forces, and so on. So that may not go much further. We also have this anomaly, which, of course, you can explain as dark matter, which is the rotation curves of galaxies and lensing and so on. And so this week I thought about, what are we really seeing here? Are we seeing dark matter? I mean, the dark matter and MON seem to be some things that people like to debate about. And whenever I use this word, several people, like Dan Carney, give me his distasteful looks. But I don't have any feelings about these things because, as I said, I'm not a theorist. So I have complete dispassionate regard for either one. I find them both to be strange. And so I thought maybe it can be some mix of these things. Is it possible that dark matter is really a hint of some type of signature of quantum gravity at the low energy scale? And is it possible that in the empty space that we have, we don't really have the ground state all over the place, but we have something like what we would get from glass physics, that as you go to a zero temperature, you actually end up with different regions of different entropy. And so in that case, you could have frustrated states that can never tunnel into the true ground state, and you're left with a bit of energy here and there in different patches. And those things will self-gravitate and clump, and I don't know about any limits on this, but I just bring it up just to entice arguments. So what about a concrete experiment? So I thought, but this is, although Yanbei is a co-author on this paper, please don't blame him. This is just a formula that I write down and he laughs at. But for a simple-minded person, this is what you can do. And so I thought, I understand, again, like I sort of understand glasses, not really. Philip would say not really. But I would say macroscopically, I understand glasses. I understand what their behavior. And you can talk about them like this, where you say, I have a complex Young's modulus, and in here I'm sort of wrapping up my ignorance of the microstructure. And you say, you have a complex spring constant, or Young's modulus, and that encodes the fact that energy is lost into modes that I don't observe. And those are all very high frequency. For these acoustic measurements, those are all in the infrared, hundreds of megahertz, gigahertz, or sort of milli-eV level resonances. But we can access them at low energy, and that's because of their tails. Because of this mode-mode coupling in solids, you can observe this really high-frequency phenomenon at low energies. And can we do something like that for gravitational waves? And how many loss angles are there? Is it enough to talk about just one loss angle or not? Anyway, Yanbei and I shared a flight up here, so I was able to get his notes in here. If you can't read it, what this and a few more pages of notes say is that you have to be a bit careful because, of course, you do have gravitational radiation from radiation because you end up with waves on the right-hand side, or depending on how you want to talk about it, but you have things like the strain squared, which also give you some sort of loss. But this would be different, so you'd have to already calculate this, rule this out, and look for something like this. And now, what does this really mean? In solids, this is what you would call ultrasonic attenuation, or something that sound waves just don't travel forever, and you get attenuation and you get dispersion. And, well, I would say this theory is not ruled out, but there's a strong limit, and the limit is that we have observed gravitational waves. So that's sort of a ground truth we have to deal with. And there are signals that have come from, let's say, 1 billion light years ago. And the LIGO sensitivity is optimum at timescales of around 10 milliseconds or so. So that means you have something like 10 to the 18 cycles of that signal, and it hasn't been attenuated. And so if there's a loss angle in space, it's incredibly small. It's something like that, 10 to the minus 18 or so. Now, what would it mean if it was stronger? We would essentially have a screening size, and you wouldn't be able to observe anything beyond that. But as far as we can tell by looking at the counts of gravitational waves, they increase as you go out into space, as you would expect for 3 spatial dimensions. There's no extra counts, or there's nothing else going on. Things seem to be isotropic. Well, it's sad for me. I like that theory, but maybe that's not how it is. So what can we do? Are the LIGO interferometers useful for anything? Can they say anything about quantum gravity? I wonder. I'm not going to answer this question. I'm still wondering, so I bring it up. So this is the basic picture of the LIGO system. I would say you have 2 big. It's more complicated than this, but this is at this level. So if you're a child playing with lasers, this is a good approximation for LIGO. You have big test masses of tens of kilograms, and a laser field which is extremely strong. The laser power is enough such that the dominant restoring force on the mirrors is due to the laser radiation pressure, and is not to do with the suspension wire or something. It's completely. You should think about it as a rigid bar. There's masses, and the rigid bar of the light beam connects them all, so it's a single object in that sense. And the noise we deal with is due to the vacuum fields that come in through this empty port, and that's essentially the trick. A bit more complicated. We send in the light, and the reason we get such a high power is that the light lives in this resonator, and this resonator itself has a Q factor of a few hundred optically, and so say the power is built up by a factor of a few hundred, and the light that enters here is something like a few kilowatts, and so we end up with something of almost a megawatt in terms of the laser power inside. And what about the other properties? As I said, this is 40 kilograms right now, and this is at room temperature. And the pendulums, the wires that hold these mirrors, they have a natural frequency of about 1 hertz. And here, a little bit of the magic is here. So that number, 10 to the 10, for experimentalists, you sort of laugh and say, no, you've lost some zeros. You've added some zeros there. But the trick of this is gravitational dilution. And so for pendulums, almost all of the restoring force is in the gravitational field. And roughly, we can say the gravitational field is lossless because we don't worry about the reaction losses in the Earth or that sort of thing. And by a factor of a few hundred, that's true. And so this is almost a dissipationless system in terms of the center of mass motion of the optic. For the internal body modes, the quality factor is about 10 to the 8 or something like that. And perhaps we could get to 10 to the 9 or so. And it's just as I said, the vacuum noise comes in, although what we do these days, and I would say this was a really mind-blowing idea in the late 1970s, and then in the 90s, it was something like a thing that if you demonstrated, you could get tenure at a university. And a few years ago, this was something that an undergraduate could do in my lab in the course of 4 weeks. So that's the pace of this technology. And right around now, we can produce squeeze states that give you an improvement in your displacement resolution of about a factor of 5 or so. And in LIGO, it's not that great. It's maybe a factor of 2 is what we can get. The interesting thing with the squeeze states and with LIGO being so radiation pressure dominated is that you can directly excite and manipulate the optomechanical states of the system. So you can put it into the ground state at a few different frequencies. You can send in all kinds of entangled light as you want, and you can create entangled states between the different mirrors. And that's because the decoherence time of the mass itself is so long, and the sources of noise are really absent because people like me have been kind of whiling away our time for decades in the basement and getting rid of non-interesting sources of noise, which I don't talk about. But there's more that we can do. We're now looking into doing single photon detection. So if you go back here, often when people talk about this, they pretend as if it's a Michelson interferometer and that there's really no light coming out of here, but we make linear measurements of the strain. And so in fact, the two arms are always imbalanced so that we get a direct, a linear increase in the detected power as a function of strain. And we do that because you'd like to be able to say that you have a black hole of a certain mass and it sounded like this. If you have single photon detection, essentially you just say something happened. And rather than something happened, we're supposed to be doing things for the astronomer community, not just the quantum gravity community. So we make linear measurements. However, when you want to do things like test for something beyond Einsteinian gravity, the best test that you can do is something more like hypothesis testing. And so there you actually want to run the system in a dark fringe. And so you run it such that in the case of classical GR, you get zero signal. So you put in a feed-forward signal in some sense to subtract off the Einsteinian signal. And then you look for single photons to come out. And which sounds fine, but as I said, this is a megawatt. And a single photon is much less than a megawatt. And how do you get your megawatts to balance so that you have zero photons coming out of here? Well, we don't know. But that is a research topic we're addressing right now. Essentially, we have a bunch of tricks to reduce it by a few orders of magnitude here and there. And our very clever scheme is to take something that does 3 orders of magnitude and then just do it a bunch of times. And that's how we plan to get all the way down. And we're sort of now at the level where I think we can get to about 1 photon per second on a tabletop. And the next year, we're going to be working to get that down to about 10 to the minus 3. And it's mostly adaptive optics and beam shaping and that kind of thing. What about superposition states? Like I said, we have the free body modes, and those have a very high Q factor, which is nice. But people have talked about putting it into superpositions of the rigid body modes. And so you would send in entangled states through the open port, where we would send in squeeze states, and you would drive the masses into n equals 3, n equals 5, or something just slightly above the ground state in a couple of the acoustic modes of the mass, which would be around tens of kilohertz or something. So you imagine, you should not imagine it as a single mirror. Rather, there's 4 mirrors connected by this laser spring, and that entire system is resonating, and that entire system is in a superposition of 2 acoustic states, which is a combined optomechanical system. And those are available to us without too much trouble. That's the kind of thing that we could do with a few months of work. Much more challenging is really our frontier in optical metrology, which is using non-Gaussian optomechanical states. And this is just one example. So these are the GKP states of Gottesman, Kitaev, and Preskal. And the basic idea here is to say, well, here's the Heisenberg uncertainty principle, but it's really constraining the total area of uncertainty that you have. And there's nothing saying that you need to have one circle here, which we normally do for the vacuum state, or an ellipse, like we would get in a squeeze state. But rather, the uncertainty can be spread out so that you have a system which is sort of periodic in the uncertainty, which doesn't really help you unless you have some sort of prior that you can say that tells you you're not over here, in one of these funny states. But this mathematically, anyway, you can do better than squeeze state detection with GKP states. This is just one example, but the world is now pushing toward non-Gaussian states for measurement, so this is a coming topic. As Yanbei talked about, we're now considering nonlinear feedback, nonlinear coherent quantum feedback to place the LIGO interferometers into really exotic states. And I've been thinking about it for other reasons. What can you really learn from classical nonlinear feedback, and do you really need to have quantum nonlinear feedback? There's this issue. GR is a nonlinear theory, so I think this is true. This is not a result, this is just a thought. I think if you were to make essentially a self-focusing gravitational wave laser, which as it travels through space, its own energy density self-focuses it, and so you get self-focused waveguide in space. that beam itself would generate harmonics due to the potential sourced by the energy density of the wave itself. And so this thing, as it travels through space, I believe, would just generate a rainbow of harmonics of the initial signal. So perhaps you can't use this if you're really looking for a small nonlinearity. You have to calculate this and subtract it. The macroscopic objects I just talked about, so the free body modes and rigid body modes, maybe it's a nice idea, but as I look into these things, torsion pendulums and the acoustic modes of the mirrors and the cantilevers, you have to come to grips with this, that the bulk modulus or the Young's modulus in almost all solids, or all solids as far as I know, is nonlinear. And so at the level, we're looking for this small frequency splitting or tiny sidebands of a large peak, you can't honestly do it. You could talk about the experiment, but when you go to build it, you will not find a system like this unless you engineered a solid that somehow has a zero crossing in all of the nonlinear Young's modulus components. But I don't know how to do that. That's a kind of unobtainium in condensed matter physics. So Yanbei mentioned this experiment we're working on, which I'm responsible for the acronym, so send all of the hate toward me. I had to put in quantum and gravity, and the choices were QGuessed, which doesn't mean anything, and then I thought GQuest. Quest is noble, so let's use GQuest. I don't know what it stands for, actually, but it's something like gravity, quantum, space-time, anyway, all those words are in there. The idea of this model is that space-time will be filled with some sort of noise, and it will be roughly broadband. And of course, it's described by some angular and spatial correlation functions. It may remind you of the Craig-Hogan theory and the corresponding experiment at Fermilab, the holometer experiment. And I think from the outside, it looks more or less the same. There is a L-shaped laser interferometer, and it is looking for high-frequency noise. The difference is, of course, the theory is very differently motivated, and this experiment builds on that wisdom, but is something like that holometer experiment, but on steroids. And that will incorporate the latest LIGO technology and cryogenics, low noise suspension of mirrors, and then also the use of these non-Gaussian optical states, I hope. And in this one is where we're really developing the single photon detection. And so this whole experiment, although I say it's LIGO-like, it's a little bit more like a particle physics experiment because it's run on the true dark fringe, where we'll really cancel all of the steady state light and look for new photons to be generated and pass through all of our optical filters. And so we're now working on this single photon detector with JPL to get it going. No, this is a different talk. Let's see. So to conclude, I wanted to say something more about what should we do? My feelings on what we should do. How do we proceed in a way? How do we spend our finite resources to get towards actually finding something as soon as possible? And how do we do it in this space where we don't really have a real experiment yet that's, this is the quantum gravity thing that's going to really reveal this parameter. So, I mean, those of you who have ever used MATLAB fmin search, that uses this algorithm. This is the simplex algorithm for numerical optimization. And this is the idea. There's an amoeba in space, and it's sort of stretching out and looking at hot spots and cold spots and looking to see which direction should it go. And it sort of avoids the local minimum. It's the kind of thing that we're looking for, is how do you minimize or maximize something when you don't know what space are you in. And so there's a formalism for this, of course. We use the Fisher information matrix, or the inverse of the covariance matrix, to parameterize our uncertainty. This works in the case where you have a model, and you say, well, there's the universe, and it is a function of some parameters. And I'm going to measure the universe. And now I'd like to find out what experiment that I have that gives me the maximum Fisher information about the universe. Or you could say, if you take the inverse of this is something like a n-dimensional covariance matrix. And so what I'm asking to do is to minimize the volume of this n-dimensional hypervolume of the covariance matrix. And you do that by computing all of these terms and then thinking what kind of measurements you can make. An example that we do, electrical engineers know about this. So if you have a Green's function or a transfer function in their lingo, and it's governed by parameters, poles and zeros of the complex transfer function, you can ask yourself the question, given it finite energy and time, and this means our time and experimental resources and theoretical resources, how do I learn the most information in a quantitative way about this system? And it's a field called optimal system identification, and you maximize the determinant of the Fisher matrix as a function of time. And so it's straightforward if you know the parameters, because you can compute exactly how to do this and where to put your energy so that you get this. But what about this, where you have unknowns? You have places, there's parameters in the system that you've never thought about. Well, we're working on that now, and it seems like the thing to do is you make null streams, where you say, I will measure my system of 5 parameters using in 7 different ways. And I can recombine my 7 measurements such that a couple of them will always be null. I have real null measurements coming out of my system, and 5 of those measurements will tell me about my knowns, and I don't know about the unknown unknowns. But for the known unknowns, meaning there's parameters that we don't know what they are or where they are, we can use this null stream to find them. And so I propose we could put together our theories and talk about it in this way, at least to have a way to evaluate what experiments are valuable to do. And there's some background on how to do this already. So there's Cliff Will and his great program of parameterized post-Newtonian parameters that you can constrain with your alternative theories of gravity. And then, more lately, there's Franz Pretorius and Nico Yunis, who have their post-Einsteinian formalism, and I'm sure we can come up with another formalism. But these give you ways to parameterize the things that you don't know about. And the nice thing about it is that whatever theory you have, as long as it's a metric theory, you can parameterize it in this way, and you can set upper limits, and then you can quantitatively discuss whether this experiment is better than that experiment, and which one will be limited by systematics. How am I on time?
3 minutes.
Oh, good. I mentioned this before a little bit. So for this particular effect, which is just a favorite of mine, but that shouldn't have any bearing on what we actually do. For this one, I looked at how people study this for solids, and there's a few different kinds of. So for this phenomenon of acoustic attenuation, there's different theories of what it's due to, and some of it is due to two-level systems in solids, some of it is due to anharmonicity in the potential, and some of it's due to something like surface cracks and technical things like this. But people had a protocol, and they went through and they did ultrasonic measurements throughout the 1960s through the 80s, and around 1970 it was sort of shown that for large objects anyway, it was for sure the Athikari damping that was giving you the sort of anharmonicity in the solid was moving around the phonon background, and that was giving you a source of dissipation. And so there wasn't anything about there wasn't any mystery left in the solid. It just came right out from just looking at the phonon field and saying, indeed, when I strain an object that has a phonon distribution, it is now out of equilibrium. And as it moves back and forth in and out of equilibrium, there's a loss associated with it. And so they were able to identify what the mechanism was. And if we ever witnessed anything like this, we could use this also. And the Athikari damping effect is really telling you something about the microphysics that you wouldn't be able to measure directly. It's happening, it's sort of limited by the interatomic spacing. And in that way, it's a little bit like Brownian motion, where you make a macroscopic measurement, but it's telling you something about atoms. And so I'm hoping that we'll find something in this direction, where we can find macroscopic signatures of these effects, which I think most of us would, I don't know about most of it, a lot of people would say that these effects only show up at the Planck scale, or maybe within a factor of 1,000 of the Planck scale. And what hope do we have to measure something like that? I think we'd have to be creative and find places like this where there's real macroscopic effects. I don't know what country this looks like. I think maybe this looks like an elephant. So I hope this is where we're going, and I wondered about how do we actually get here. for me, what's missing in this community is a group of people who are intensely working at the interface between theory and gravity, or between, sorry, not intentional, between theory and experiment. And on the experimental side, we have a lot of great ideas about gadgets and things we can do, but we could use a lot of input in designing our experiments and help. And I think having theorists and experimentalists embedded together and trying to figure out what can be done is a very fruitful way of doing things. And I went to Caltech mainly because I knew there was this history. Vladimir Brzezinski had been coming there since the 70s, and working together with Kip Thorne, they had made this team where there were experimentalists and theorists eating and living together and designing experiments. And the great power of that group was that no matter what else was going on, and people were thinking about black holes and whatever, occasionally you'd have a person like Yanbei Chen would show up, and he would take a break from his black hole business and come over to our side of the building and help us design interferometers for a while. Yuri Levin did this, Carl Caves did this. It was great. And those people who did that work in the 1980s, or in the 2000s even, when I first looked at Yanbei's stuff when we were in grad school, I said, who cares? And that's nuts. And that's ivory tower nonsense. But now, it's actually what we use to operate the system. It's a daily function of the system, and people are still looking at that paper from 2001. So we need more of that. And how do you do it in a focused way? I think this is the perfect kind of place to do it, where people come and get together for a couple of weeks, and you just focus on this topic, which is, I'm going to come up with what are the top 5 experiments to find signatures of quantum gravity broadly, not just for my own theory, but for whoever has whatever theory. And let's just get it done. And we have to do it in that kind of focused way, because I don't know enough about gravity or no-go theorems, and I think Yanbei doesn't know enough about like op-amps and vacuum systems. And so we somehow have to share our knowledge. But my hope is eventually we're going to make this thing. And you see, in this picture, there's no snakes and there's no sharks out there. There's just more islands. And we'll just hop between these different islands and eventually get there. And these are unsatisfactory, but look at this. I mean, how can you not fall in love with this? Thank you.